There was something wrong. I think it's rebooted or something. Okay. Okay. Is it all good? Yes. Okay. Okay, let's get started. Oh, this is a bigger room. Can we use this room for Thursday also? It's occupied already? Yeah. Okay, today we're going to continue memory-centric computing. Let's see if we finish it. If we don't finish it, we'll start robustness next time. Okay, if you recall, we were discussing two approaches to processing in memory. One is processing using memory, which we're done with, which is really the ability to exploit the analog operational characteristics of any memory to do computation. And there's a lot more to do in that direction, I think. That's a fascinating direction. And the other direction is more, let's say, conventional, but still pushing the computation to the data, meaning putting logic units, computational logic units, closer and closer to the memory arrays. So we were discussing processing near memory, and this is a reference paper that you may be reading. And we were treating memory as an accelerator in both approaches, if you remember. We discussed the tesseract system for graph processing. I'm not going to go over that again. This may be one of the papers that you read and analyze. We discussed accelerating neural network inference. And we discussed that when you do processing near memory, it makes sense to take a top-down approach and think about what applications can you accelerate and what can you accelerate within an application. And this was a high-level overview, which I'm not going to go through again because we discussed yesterday. And we stopped around here yesterday. Are there any questions from yesterday? Anything that came to your mind that you may want to discuss? No? Everything good? You can answer any questions from yesterday? Okay. Are the lights too much here? Would you try a different setup? Let me see. Better? Hopefully people won't sleep. Projection, low light. Okay. For me, this is better, but I don't know for you guys. Is it good in the back? Okay. It was too bright earlier. Okay. Now I'm going to go through some other examples of this, and then we're going to talk about some adoption approaches, adoption issues, and then we're going to talk about some real processing in memory systems that have appeared since 2019, and then we're going to conclude. This paper, actually, you're kind of familiar with. I mentioned some quotes from this paper earlier. This is one of the early works that we did with Google in 2016, 17. It was published at 18, as you can see over here. But we wanted to understand the potential of processing in memory in consumer devices. And clearly, consumer devices are important, and energy is a huge issue in consumer devices. And we wanted to see where the energy is going in these consumer devices. So we examined these four major workloads, which people use today. Actually, right now, because we're streaming things on YouTube, these video playback and capture engines are working. The Chrome browser is working perhaps, or some kind of browser is working perhaps on people who are watching the stream. And I'm sure some machine learning frameworks are being run also on these things, right? Like people these days run machine learning frameworks in meetings and summarize the meeting without thinking about privacy implications of that, I guess. I guess if it makes your life easier, you don't care about privacy. I don't know. Not true. Okay, but we looked at these workloads and we did a lot of analysis. You can read the paper for more detail. And one of the observations I've already given you, basically, we've shown that on average use cases, average inputs for these workloads, more than 60% of the total system energy is spent on moving data between the DRAM to the CPUs and the SoC, back and forth, basically. And then we wanted to understand how we can actually reduce this data movement and what kind of benefits we would obtain if we do so, if we actually place compute units near DRAM, meaning in the logic layer of 3D stacked memory in this particular case. And the paper has some analysis. One of the issues with putting computation in a logic layer underneath memory layers is thermal issues, right? Because if you put computation and memory on top of each other, now you have heat that has nowhere to escape. In current processors, it's two-dimensional. You don't have 3 dimensions. Well, in some existing ones, you have 3 dimensions. But if you have two-dimensional processor, the heat can escape from the top, and you can actually remove the heat using a heat sink, right? But if you have multiple dies stacked together, then there's no place for the heat to escape unless you actually have a cooling solution between the dies, which tends to be expensive. So in general, not employed. So you have a thermal problem in these chips. So you cannot put any kind of computation unit in the logic layer, because if you put a, let's say, 4 gigahertz or 5 gigahertz computation unit that's consuming a lot of power, then you have a thermal breakdown in the entire stack. And that's not allowable. So this paper does some analysis on what can you put given the thermal limitations that we envisioned at the time. And in the end, as you will see, we put some accelerators or in-order cores, simple cores. I shouldn't say in-order cores necessarily. But basically, the second key observation, it helps us, along with the thermal considerations from the underlying technology, second key observation that we have enables us to decide what should we build as accelerators or as general purpose cores. And the second observation is interesting because we found out that a significant fraction of the data moment often comes from simple functions, at least in those workloads. And we said that you could design lightweight logic to implement these simple functions in memory, meaning the logic layer. So it could be done in a small embedded low power core. And we analyzed that in the paper. Or you could actually implement small fixed function accelerators to implement these functions, right? Especially if the function is used by many workloads, it could be useful to have fixed function accelerators. Of course, the downside of a fixed function accelerator is if the function is not used in a workload, then you turn it off. Right, that's not very good. And there's actually some other space over here that we did not fully explore, which is you can have reconfigurable logic that you can configure depending on the workload that you have, right? Later works we explore that, but not in this one. Okay, so the takeaway is that if you do this a little bit carefully, then offloading these simple functions that are data moment dominated to the processing in memory logic, it reduces energy and improves performance by more than 2x, essentially. Which is not bad, right? Because we're not changing the system a lot over here. In the Tesseract work, if you remember, we were changing the entire system. In the later CISA work, we were changing the algorithms as well as the system. Okay, just to give you an idea, there's a lot of workload analysis in the paper, but I don't want to spend a lot of time over here since you may actually have later lectures on this topic. One example is TensorFlow Mobile, where you do machine learning inference. You have a deep neural network that does inference. And we found out that based on analysis, more than 50% of the inference energy is spent on data moment. And more than 50% of that comes from very simple functions like packing and unpacking of data when you actually move from one layer to another layer, for example. And also quantization, which is used in essentially all neural networks today to reduce the energy consumption and improve performance. So normally you don't operate with large data widths, as we discussed yesterday, kind of. But you actually, even though you may store large data widths as inputs to the network, you can quantize them to much smaller data widths and data types. And sometimes even change the types from floating point to integer, for example, so that you actually reduce the amount of data moment and energy. But when you're doing that, that actually causes data moment itself, right? Quantization itself causes data moment, and it's a lot of data moment. And in the paper, you can see more analysis. So without going into a lot of detail, you can design, these are the functions that we thought were important to optimize and push to the memory side in this work. For example, in the Chrome browser, when you're doing switching between the tabs, usually if you have a lot of tabs, then what happens is Chrome browser stores some of the tabs in compressed manner in memory because you may have hundreds of tabs, let's say, and then some of the you won't have enough memory to store those tabs, right? So it's compressed in memory using something called ZRAM or some other algorithm. It doesn't have to be ZRAM, but it's ZRAM in this particular case. Now you can actually when you're loading a tab, you need to decompress it, and this tends to be on the critical path. And accelerating this actually reduces the critical path and also improves energy. This is showing energy. And if you do it on a general purpose embedded core, you reduce energy significantly. If you do it on a more specialized accelerator, you reduce energy a little bit more. Okay. So specialized accelerators are always better for energy as expected because they're really specialized for the function. And you can see there are other examples like compression. Compression can be accelerated also because it's a very data intensive task. There are also other things like when you're loading a page, you need to tile the textures and do the color billeting, etc. And these are the two functions that I mentioned. And then there's some other function in video playback and capture that I don't want to go into right now. But you can see that people actually design hardware accelerators on the CPU side for this, but we were looking at things on the memory side. And runtime also reduces, as you can see over here, significantly. One of the interesting observations in this paper is both runtime and, something happened here. Both energy consumption and runtime reduce around the same amount, basically more than 50%, or if you just change the way you think, it's about 2x, more than 2x. Okay, any questions? The paper has a lot more analysis. I'm giving you a broad picture. Yes?
Would you say that the change from PIM core to PIM accelerator is strong enough to motivate a case for PIM accelerator? Because it looks like a small fraction.
I mean, it depends on the workload, right? And for example, if you look at compression and decompression, the latency reduction or runtime reduction is significant. Does that make sense? It depends on the workload, I think. Maybe energy reduction, there are still places where the energy reduction is also significant, but I would say depends on the workload and depends on how common the function is across many workloads, right? I can see compression and decompression can be generalizable accelerator that could be used for multiple potential algorithms. But maybe some of them are very specific, although people are already building it, right? People are already building video encoding and decoding accelerators. So why not on the memory side if you already built it? But that's a good question. That's always a question, like, do you want to design a fixed function accelerator or a reconfigurable unit that you program online or offline, or somewhat programmable accelerator? Yeah.
Did you design a specific accelerator for each of these?
Yes. Yes.
Or would it be like a general purpose?
Yes. It's a general purpose ARM core, basically, PIM core. Yeah. It's a low power one. It's not like very intensive. Okay, you can read the paper. I think this is one of the papers that is assigned. And I like this paper actually because it does a lot of analysis on real workloads that are really used by people, and also tries to really nail down where the energy is spent, where the performance is spent. I didn't actually talk about where performance is spent, but it's also memory mostly, but it's in the paper. And some of the hardware that we use actually for the video playback and capture are actually hardware accelerators that Google designed and they're using in their systems. If you actually read, Google had a paper a few years ago in ISCA where they talk about their video encoding and decoding accelerators that they employ in their data centers. They do it because they get a lot of videos, right? Well, YouTube is one example clearly. And they need to actually store these videos and also play back these videos in an accelerated way. So they have a lot of accelerators for not just video playback and capture, but also compression and decompression of the videos themselves. Okay. Okay, so switching gears, let me talk a little bit about in storage. Basically, yes.
So these accelerators are based on connected to these storage.
Could you say it again? I couldn't hear.
The accelerators which are created for them.
So these are, what we did over here was on the main memory side. Basically, you put, that's the evaluation. But there's no reason you cannot push the accelerator on the storage side also. You just need to modify it to fit the constraints. Okay, I'm going to switch gears and talk a little bit about storage. I mean, processing near memory, as I said, memory and storage are very similar to each other. For me, actually, that dichotomy should not exist. We're going to talk about that later on. But accelerating things on the storage side is also very interesting because moving data from a storage system to the memory system is actually consumes a lot of power and a lot of time as well. So if you could actually do a lot of processing on the storage side without moving data from the storage to the to the memory and then the caches and the processor, then it can actually eliminate a lot of the overheads. And in fact, storage system is very interesting. When we talk about storage, you will see that the storage system itself is a system today, meaning you have real processors, full processors to control the storage system. because these are really controlling access to the storage system and making sure that the storage system works correctly for multiple ways. And also you have memory inside there, not huge memory, but a little bit of memory so that the storage system is not overwhelmed with the requests. It's used as a cache or mapping buffer, etc. And then also storage, which is SSDs. So you really have a system inside a system if you think about storage. So why not make the storage system the system and get rid of everything else in the system? I like this sort of thinking. This is more storage-centric computation. And this is an area that we're exploring heavily right now. And I think actually that would eliminate some of the efficiency in the system if you actually get rid of the system inside a system part. But talk to me if you're interested in that. But let me give you some concrete examples of what you can do in the storage system without like getting rid of everything else. So clearly you can use storage as an accelerator also. So, and we're going to look at genome sequence analysis. Later, we're going to have some lectures on genome sequence analysis, which is a fascinating area, which generates a lot of data. And in this case, you have a lot of data, and the data may not even fit in main memory in some cases. We'll see that in the next work, especially. And what happens in genome sequence analysis, you normally move data from the storage system to some computation unit to do the analysis. And usually the analysis is some sort of approximate string matching. You basically have a reference genome, and you sequence somebody's genome, let's say, and you try to map the pieces, because normally sequencing happens by chopping the sequence genome into pieces, and you try to map the pieces to a reference genome. This is really text matching, approximate string matching, but you'll see a lot of exciting things in later lectures. This is called alignment, essentially. Text matching with some errors allowed. That's enough for you to know right now. But you need to move a lot of data from the storage system to the computation unit if you have a lot of sequences coming in. Clearly, this causes computation overhead because that approximate string matching with errors allowed is actually costly in terms of computation. Especially depends on the number of errors. As the number of errors increases, the computation complexity also increases significantly. And there's a lot of analysis on that because this is done by dynamic programming usually. And also there's data movement overhead on top of the computation overhead, right? So what previous works do is they use heuristics, accelerators, and filters to actually minimize the data movement and at least minimize the data movement from main memory, because there are a lot of processing in memory accelerators. In this case, I'm looking at the storage system, as you can see. And also they do a lot of optimization to accelerate the computation. So this usually addresses the computation overhead, but this doesn't address the data movement overhead from the storage system. And that could be the bottleneck, especially if you have lots of things to move. So this work, it's called GenStore. The key idea is very simple. The key idea is to divide the tasks so that some computation is done over here, and hopefully little computation is done over here. Basically, the key idea is to filtering again. Filter the reads or sequence that are coming in that do not require expensive alignment inside the storage system. And basically, the idea is do some of the computation over there so that you move the data, you move a little amount of data over here. And the hope is that you find computation easy to align things over here and do the more complex tasks over here. That's the idea over here. So let me give you an example of what is easy to align. Meaning you have a sequence, let's say it could be, I don't know, 1,000 base pairs. I'm just picking that number. You're trying to align that to a 1,000 elements or 1,000 letter piece of the reference genome. This is very easy to do if these two exactly match each other, right? That computation is very simple. If you actually want to see if two things exactly match, you can think of an XOR tree. That's not the best way of implementing it, but XOR tree is one way of implementing it, okay? There could be other ways. So, but this computation is easy to do. So if the source string and the destination string are exactly matching, you don't need expensive dynamic programming algorithms for approximate string matching. So do it in the storage system. This is a very easy to design accelerator also. And also the things that are easy to do in the storage system is completely different things. So if the source and the reference string don't match each other with a huge error rate or huge difference, that's also very easy to detect in general. You can, for example, look at the differences in hash values relatively easily. I'm just giving some ideas to you, but there's another way we do it over here. The really difficult part is somewhere in between. And the idea is to, if these are not filtered using the accelerators that are designed for exactly matching and non-matching, then ship it to the computation units that are doing the expensive computation, okay? And if you do this, you will address hopefully most of the data movement overhead from the storage system. And the paper shows that you can get significant speed up as well as energy reduction at the same time with low cost modifications to the storage system. So this work, basically the idea is to actually do minimally, well, not minimal, but change the storage system as little as possible so that you get performance improvements. But then there's another way of thinking about it. How would I rethink the entire storage system to actually get even higher benefits? And that's an area that we're working on right now. And you can see that the speed ups, of course, depend on the use case and what fraction of the inputs are actually exactly matching or non-matching. So if you have no exactly matching or no non-matching ones, then clearly you're not going to get any benefit. In fact, it's going to be worse. But that's not the case in many bioinformatics workloads. Usually, especially depending on the analysis you do. For example, my genome and any one of you's used genomes over here match by more than 99%, actually 99.9%. The variations between our genomes what make us different, both in terms of how we look like and also what we are vulnerable to, etc., how we would react to things. If you compare my genome to a banana genome, that's about 60% also. Yeah, it's interesting, right? Sometimes I feel closer to a banana. Okay. Okay. Okay, so this is the idea, and you can read the paper for more. More recently, where is Nika? I think she's still sick. Nika actually led these works. Is she online? I guess she's so sick that she cannot even be online. Okay, this is a more recent work that was published at more recent ISCA, like in July. I'm going to go through this relatively quickly because we'll probably have a more detailed session. But this is just to show that you can actually, genomics data is actually exploding. There's a lot more data coming into the storage system. And this work is the first in-storage system for end-to-end metagenomic analysis. I'm going to describe what that means. And it basically provides a hardware-software co-design between the storage system as well as the host system, and partitions the work between these two systems so that you can get an energy-efficient and high-performance system for metagenomics. And you can see some example of the storage system better over here. It's complicated, basically. In an existing storage system, you have a bunch of cores. You have the flash translation layer, which has specialized hardware, and you have the controllers, which have specialized hardware, and you have a DRAM, which stores some metadata, and you have the real flash chips over here, essentially. So it's really, when I said it's a system by itself, you can see that it's a system by itself with accelerators over here for specialized for storage, general purpose cores, and actual controllers for flash, and then DRAM and controllers for DRAM, which is not shown over here. Okay, so what is metagenomics? It's really one way of doing genomics, but normally you have the reference genome, but here you don't have a reference genome, meaning you sample something. So for example, I take a sample from this desk and I put it through a sequencer and I try to figure out what's on this desk, right? You could do it. I don't want to find out probably because I've been touching it for a while. So you could do it. So what happens is you take a sample, and these samples are actually when it goes through a sequencer, it gets chopped into pieces. And now the goal is to compare these pieces to a database, a huge database that may contain many species, right? Thousands of species. If you want to be completely comprehensive in figuring out what's here, you really want to compare it to any known reference genome, right? Clearly, in some cases, it won't match closely. In some other cases, it will match significantly, right? And so this is a huge reference database containing many species. And metagenomics actually is to, the goal of metagenomics is to identify what species is here and at what fraction. That's the abundance, basically. So there are multiple steps over here. You need to prepare the input queries by chopping them into pieces appropriately. And then you need to, this step 2 identifies what kind of, let's say, what kind of reference genomes these prepared input queries actually match. And then this abundance estimation says what fraction, at what confidence level I think there are species from these different reference genomes in the sample. Okay, without going into a lot of detail, this really, you really need to partition and map the tasks between the host system and the SSD. And this work does that. Step 1 it executes on the host system because it's not as data intensive. Step 2 and step 3 execute over here. And then you need to coordinate data and computation flow to reduce the communication overhead. And one of the issues with the SSD that we will talk about later is writes are expensive, because when you write to a flash chip, NAND flash memory, you wear out the memory. And as you write many times, the memory wears out. At some point, you cannot write reliably, meaning you cannot read the data that you write. This is called the endurance or wear out problem in non-volatile memories. And it happens not just in NAND flash memory, but it happens in phase change memory, for example, and many other non-volatile memories. So clearly, you have limited write cycles or limited endurance. So you need to be very careful when you're doing computation near flash or in flash. If you keep writing to memory a lot, then you're actually wearing out the memory, right? That problem doesn't exist in DRAM, at least as far as we know, at least to the extent that it is there in NAND flash. In fact, in NAND flash, for example, with the state of the art, I think it's quad level cell, right? Today, quad level cell memories, you can write to one cell at most 100, 200 times maybe, if you're lucky. So it's very small, as you can see. It used to be much larger with single level cell and also larger cell sizes. This is one of the technology scaling challenges in flash memory, actually. Well, we'll get to that later. But basically, you want to reduce writes to flash chips when you actually coordinate this data flow and also change the algorithms. So there are also storage aware algorithms to enable efficient access patterns to the SSD, minimize random access as much as possible, maximize streaming accesses because they're faster, as we talked about. And also, to accelerate computation, we have some hardware accelerators over here, which you will read about when you read this paper. And also, these hardware accelerators, you need to design them carefully to minimize the buffer spaces needed in the SSD. We're still trying to minimize the changes to the SSD over here for adoption reasons, right? And finally, you need to also have a data mapping scheme and flash translation layer that's kind of specialized to this sort of computation, which I'm not going to talk about. So clearly, this is also a full system level paper, and there's a lot of detail in the paper. Let me give you some results just to motivate. When we talk about this paper, you will see more, but this sort of study is not easy to do in a real system. We're trying to do it in a real system, but real systems don't have the flexibility to do this sort of computation. Hopefully we'll get there at some point. But we do a lot of simulation, as we've discussed at some point. We use the simulators that we have developed. We're going to talk about that more, maybe, during the course of this course. And we compare to both software baselines and hardware baselines, as you can see over here. And there are a lot of results in the paper, but in the end, some software baselines improve performance at the expense of accuracy, because this is always a trade-off. It's a very fundamental trade-off. You can always improve performance if you ignore some bits, right? That's performance accuracy trade-off. And this is sometimes done in real software because this is an application that tolerates, depending on the use case, some errors, right? If you're slightly wrong in the number of like abundance, for example, of this thing, but if you get the big picture right, maybe it's okay, right? Depends on what you're looking for. On the other hand, if you're really looking for a specific variation in a gene, then you got to be extremely accurate, because that may cost someone's life if you misidentify something, right? So it really depends on the use case. So some software baselines say, oh, I want performance, I want to do this quickly, so I don't care about accuracy. But then there are some software baselines that are accuracy optimized. So clearly, compared to accuracy optimized, we didn't want to compromise accuracy in this work. In general, I think it's good to look at both accuracy optimized and performance optimized ways. So compared to accuracy optimized software baselines, the performance improvement is a lot higher, as you can see. And also, we also look at both cheaper and expensive SSDs. So this is cost optimized SSD, so the performance improvement is much higher. But if you have an expensive SSD, performance improvement is still pretty high, but less than what you would get in an expensive SSD. What differentiates an expensive SSD and a cheap SSD? It's essentially with the bandwidth that you have from the SSD. Capacity is also an issue, but we will discuss that later. Okay, so this is compared to processing in memory baseline. Again, the improvements are still significant compared to processing in memory. And remember that processing in memory actually, at least this incarnation of processing in memory, particular processing in memory, compromises accuracy. Okay, different input sets. I'm going to skip this one. And then there's power analysis. I'm just giving you this one because this is to show you that you got to do a lot of things to actually vet an idea. And this is, I see this as a more system level paper like Tesseract than maybe some of the other papers. But there's a lot of evaluation that you need to do to convince people that the idea may be worth exploring into the future, right? Okay, I like this picture. I want to show this because I think this makes an interesting point. So we're looking at here two systems, cost-optimized system and performance-optimized system. Cost-optimized system has a cost-optimized SSD, low bandwidth, and very small DRAM, 64 gigabytes. And performance-optimized system has a high bandwidth SSD, performance-optimized SSD, and 1 terabyte DRAM. Clearly, this is much more costly, right? Now, if you actually compare a cost-optimized Megis or building Megis on a cost-optimized system, it outperforms clearly the cost-optimized baselines, but it also outperforms significantly the performance-optimized baselines. So this is actually interesting. This kind of, I think, points out the inefficiency in which we're building our systems, right? An existing system with 1 terabyte DRAM and expensive SSD cannot outperform a much cheaper system with not so expensive SSD or cheap SSD and only 64 gigabyte DRAM. It's good to think about that, right? So maybe we're designing our systems in a terrible way that a lot of the resource usage is so inefficient. And if you actually push the computation to somewhere else, your system can be really simpler. It's good to think about that, right? This is what I mean when we talk about processor-centric systems cause a lot of waste. And I think this is one example proof. And I think going forward, it's good to see this sort of comparison in papers. Just to encourage everyone who's doing research to do this sort of comparisons. Okay, basically, this is one conclusion, but the other conclusion is what I just said. Maybe we have a lot of inefficiency in a baseline system because it's not able to do computation somewhere else other than the processor. Okay, there's a lot more in the paper that I'm not going to talk about, but you can find it online. And this is very recent work. If you're interested in this sort of research, please talk to us and Nika and Mohammed over there. We're quite excited about pushing computation to the storage side and really optimizing the entire system as opposed to the processor. Okay, and this is the paper that we build on. So we actually need to simulate storage in a lot of these works, and you can find more information. This needs an update, MQSIM 2.0. Okay, any questions? No? Okay, I'm going to keep going then. If you want me to stop, then you got to ask a question. Okay, so now we're going into a little bit more adoption issues, which is you need some tools to decide what to execute where if you really want to partition workloads across, for example, CPU and storage or CPU and memory and storage, right? And I think this is an important direction. This is an area where we develop tools. Geraldo, who was here yesterday, developed this tool called DAMove. And I think this sort of tool is really important, and we really need to develop more and more tools in this direction. So that's the key idea, basically. There are a lot of studies, some of which we discussed, some of which we did not discuss, show that near data processing is actually quite beneficial. It provides orders of magnitudes in some cases factors of improvement in performance and energy. But then the question remains, what should be executed where and what should be offloaded? So it's good to do workload studies, and this is a study that Geraldo did, which comprises a lot of workloads, as you can see, more than 300 workloads. Ask him how he did it with performance analysis tools. And then I think he analyzed 77,000 functions, and he honed down to a small fraction of those functions to really understand the bottlenecks. Because not all those functions are bottlenecked by memory, for example. There are some functions that are simple, they're bottlenecked by computation, but they don't take a lot of time. They may not be that interesting, right? The functions that are really interesting are the ones that are really bottlenecked by data because they take a lot of time to move the data between storage and processor, or memory and processor in this particular case. So in the end, this is one way of classifying the bottlenecks, right? It's good to do bottleneck analysis in your workload so that you can understand what is a function bottlenecked by, right? And then you can expand this analysis to what is a group of functions bottlenecked by. And then you can decide what should be executed where, right? This is, so in this particular case, there are 6 different bottleneck classes, as you can see. The function may be bottlenecked by DRAM bandwidth, may be bottlenecked by DRAM latency, may be bottlenecked by L1, L2 capacity, L3 cache contention, L1 capacity, and compute bound. It could be compute bound. And these are determined based on 3 simple metrics. So it'd be good to have a profiling mechanism that can understand these 3 simple metrics. So 2 metrics you've already kind of discussed. One is arithmetic intensity, essentially how many operations you do on a byte that you bring from memory. The second is the last level cache misses per kilo instruction. Basically, how many misses that you get, how effective your last level cache essentially. And the first one is the metric that this paper introduces, which is kind of an odd metric, which is last to first miss ratio. This profiling is done on a CPU. It has a last level cache and a first level cache and a middle level cache. And this last to first miss ratio is a metric that says, what is the miss ratio on the first level cache and what's the miss ratio of the last level cache? And what is the ratio of those ratios? And if that ratio of those ratios is low, that means that maybe you're going a lot to memory, right? And if it's high, that means that last level cache may be effective. And it's capturing things in a different way than MPKI, but you should talk to Geraldo about it. Okay, now once you actually identify these bottlenecks, then the question is what do you need to do? And it's not a simple answer even after that, because maybe DRAM bandwidth bound, usually offloading to processors, offloading to the memory side is actually a good idea. I think the paper shows that. But it really depends on also parallelism that you have in memory. So it's not just a function of what you're bottlenecked by, but it's also a function of how much parallelism that you have on the memory side. So it's good to think about maybe tools going into the future that capture these things in a much better way. So this is one step in that direction. As far as I know, this is one of the first steps in the direction, because people used to say, oh, we just look at arithmetic intensity. We just look at misses per kilo instruction and take some action. This paper shows that it doesn't work very well. You really need to look at the bottleneck classes. But I think there's a lot more room to improve on this one, because I think there may be other bottleneck classes to discuss. And also what this doesn't discuss or clearly specify is what kind of mechanism that you would benefit from if you do near data computation. Maybe there should be other than bottleneck class, maybe there should be a class of things that could accelerate this computation, right? It'd be good to somehow match functions to the class of things that you could accelerate this computation. And if you actually have that sort of thing quickly determinable, then you can actually have a very nice way of partitioning things. I think that part is definitely missing, class of things that where you could actually accelerate this computation in a nice way. That part is definitely missing, I think, in literature. Okay. Okay, and this is open source. People have been using it in the world, and you can also, if you're interested, take a look. You can talk to Geraldo. Okay, and then we have other tools like Emulator 2. This is not designed for PIM yet, but there's an effort to actually put PIM processing in memory capability into Emulator 2. And some of you are actually taking up on my assignment and doing the assignment, so maybe you're interested in looking at PIM for Emulator 2. Yes? Yeah, exactly. There could be other metrics basically to add over there. Yes. Yeah, MPKI is a very simple to compute metric, but it doesn't take into account memory level parallelism, for example, because if a lot of your misses are parallel, maybe you're reducing the impact on the execution time. Yeah. Exactly. I think last to first miss ratio kind of captures some of that actually in a weird way. I cannot fully explain that last to first miss ratio. You should talk to Gerald. Okay, but there are definitely other things that affect performance, like parallelism, and those are not taken into account in all. This is not an easy area. It's good to think about like what can you, like what metrics do you look at to do quick offloading, right? There's no silver bullet there at this point. Okay. So I think in the end, we need to revisit the entire stack. That's my whole point about these processing and memory lectures. So the whole stack is designed in a way that's not memory-centric. It's very processor-centric. And what we're trying to do is really like attack the stack with a memory-centric mindset. For example, we talked about mapping data, right? If you map data in a way that's beneficial to the CPU today, you try to put different cache lines to different channels, for example, or different banks. But this is not a good way of mapping data if you're processing consecutive data elements in memory, right? Ideally, you would like to aggregate consecutive elements inside each bank or inside each channel, at least, to do computation. So mapping of data is actually one thing that's very processor-centric in today's systems, and it has to change if you really want to do processing in memory, coherence, virtual memory. So this brings me to the next part, which is adoption issues. But I also should say that I think we don't need to change everything right away, right? You can get there step by step, right? Some of these ideas that we've discussed yesterday, like doing copying in memory, starting to offload some small functions, small but important functions to the memory side can enable things to change in an evolutionary manner as opposed to a revolutionary manner, which is never going to happen, in my opinion, easily. Okay. Yeah, so we have papers that talk about some of these. Now let's talk about adoption challenges. We've been talking about some of these with your questions and other things also, but now I'd like to take a little bit more time to discuss some of these challenges. And there are a lot of these adoption challenges. So clearly applications and software are important. What applications benefit? How do you write the software? How do you make the programming easier? What kind of interfaces do you provide for the programmer? What kind of compiler support do you provide? What kind of hardware support do you provide? These are very big questions, actually, right? We've been looking at a lot of applications. I'm going to show you more, actually, but programming, we've been looking at programming also. System and security support. How do you handle coherence? If processor and the memory or compute-capable memory are both modifying the same thing, how do you ensure that they don't get the wrong result, right? Synchronization is important, especially if you're offloading something and programs need to synchronize with each other. How do you actually make sure, or threads need to synchronize with each other? How do you make sure they synchronize efficiently on the memory side, for example? Virtual memory, we're going to discuss that a little bit, but this is a huge mess. Maybe Konstantinos will give some virtual memory lectures. Are you still trying to fix virtual memory? Good luck. It's a tough proposition. And then isolation is another thing, meaning if you actually have multiple things executing on the memory side, how do you isolate them from each other? And can you actually have benefits from isolation is another thing, right? If you, well, there are two reasons why you would isolate, right? One is security, so that one program that's executing in memory cannot touch another program's memory. Who's responsible for that, right? If you don't have virtual memory, then you may not be able to provide isolation over there. And then you may want to actually provide isolation to these programs and separate them as much as possible so that you get better quality of service when you do acceleration, right? And then how do you communicate between things like interfaces? And then there are a lot of ... because I'm sure I'm missing the things over here. And then there are other issues like runtime and compilation issues, like how do you schedule computation? If there are multiple things that are trying to use the same bank, how do you do that scheduling, right? This could be the CPU trying to use the same bank as the in-memory processing workload. Or it could be two different in-memory processing workloads. How do you do the data mapping? How do you do the access sharing and control, ... again. And I think finally, infrastructures are needed to assess benefits and feasibility. That's why I kind of talked about infrastructure also in the previous slides, right? So there's a lot over here. I think most important, most difficult part is really the mindset, especially for like industry adoption, because industry is clearly in a mindset where it's business as usual, right? If they don't change anything and they can still make a lot of money, that's their ideal point. Right? But we've already discussed that this is not our goal, clearly, because that money may come, that approach, that business as usual approach can come at a huge cost. And I've already given you numbers, and I believe it's coming at a huge sustainability cost today also. But I should also say, I'll give you an anecdote over here. I attended, when I was a PhD student, I attended a major conference, ISCA, International Symposium on Computer Architecture. And at that time, the keynote speaker, at least one of the keynote speakers, was Arvind. How many people know about Arvind here? Okay, that's good. It's a very common name, but I'm talking about a specific Arvind. And from MIT, okay, you got the right Arvind. Yeah. Arvind was a professor at MIT until recently. He passed away, unfortunately, this year. But Arvind did a lot of work. Actually, he gave a distinguished lecture here. I invited him a few years ago. So unfortunately, you guys missed it. Well, some of you didn't miss it. I think some of you were here when he was here. But he gave this keynote, and he did a lot of work on, he and his group did a lot of work on data flow architectures, right? So their goal was to really enable data flow in a major way, change the paradigm, because existing architectures are actually quite control flow based. And they wanted to really enable these architectures where even the programs are written in a data flow manner, right? If you took DDCA, you know that data flow actually had a lot of impact, except not the way they envisioned. They envisioned that everything should be data flow. Programs, compilers, operating systems, everything's a data flow graph actually, Like you can even represent us as a data flow graph, right? My motion, etc., the cell motions, and then everything is an interacting data flow graph, which is an interesting way of thinking about the world. But of course, he preferred to draw the boundary for computing. But I think it's more generalizable again. But I mean, going back, existing processors clearly have a data flow component in them, right? Out of order execution process. But what he said in this talk was, we did a lot to advance this paradigm, data flow paradigm. But I think we didn't do enough. Where we failed was really to fix the real adoption issue, which is really the software. We should have done a lot more work on software. So basically, I think another way of thinking about this is you can design any hardware. If the software is not able to take advantage of that hardware, then it's useless. And I strongly believe that. I strongly believe that you can do anything actually in hardware. Hardware is actually very flexible and versatile. Of course, it's a matter of cost. There are constraints over there also. But in the end, if you don't get adoption from the software, whatever you do is useless. Useless in the sense that, in the adoption sense, of course, right? People will not use it in that sense. It could be useful for academic purposes. It could inspire someone else to do something else that will be adopted in the future, of course, but that hardware itself may not be adopted by people who use software. So I think that's true, actually. It's important when you actually especially have something disruptive, something that changes how the software should behave, then you really need to think about how do you actually enable that adoption. And that's one of the reasons why we focus a lot on programming these systems, compilation for these systems, or tool support for these systems, or infrastructure support, basically everything over here in this picture. Yeah. I was going to say something else, but it escaped me. Any questions? I'm going to go through some of these issues in a little bit more detail. Okay, maybe that's something else will come. Okay, that's why we need to revisit the entire stack, but we also cannot ignore adoption. And the step-by-step is really important, I think. Okay, but the good news is, I think some of these adoption hurdles are being slowly, let's say, picked at or attacked, meaning that industry is also looking into this and they're actually producing chips. We're not in 2018 anymore. We're not in 2013 when we were doing these early studies, etc. We're in 2024, and there are already a lot of prototypes out there. And I believe these will increase over time as well. So let me give you some examples of what we thought and what we think. Well, this was what we thought in the past and what we think more recently also. I'm going to cover a couple of these and then we'll take a break. How to keep it simple. I think keeping it simple is really important. And when we actually first started thinking about this, we also said, in addition to rethinking the entire system, we should also think about like Tesseract work, right? We said that, we would like to modify the entire system to get benefits for important applications like graph processing. We also at the same time said, maybe we should also look at the exact opposite approach, which is a minimalist approach. How can I minimally modify the system such that I get some benefit? And that's the idea in this paper. And I like this paper. Even though maybe its benefits are low, I think this the beauty of this paper is really in its thinking and its approach to the problem. Okay, so this is a very busy slide, but basically our key idea was to get the most of near data processing with minimal cost, minimal change to the system, and no changes to the programming model. We said basically sequential execution should not change. So whoever programs with sequential execution magically gets some of the benefits of near data processing. That was our goal. And the idea here is, there are two key ideas actually, both of which people have improved over time. One of the key ideas goes into SIMDRAM, for example, later on. SIMDRAM uses PIM-enabled instructions. If you remember the SIMDRAM work yesterday, it uses bulk bitwise operations. And the second idea is, well, let's look at the first idea. First idea is expose each PIM operation as a cache coherent, in this particular case, virtually addressed host processor instruction called PEI that operates only on a single cache block. Now, it's a bit different from SIMDRAM, as you can see. The reason we did this is to make sure that the instruction doesn't change. It's an instruction very similar to an existing instruction, except we could also ship it to the memory side. Right? So, for example, you have a PIM-add instruction, and programmer can do this, or the compiler can compile into something like this. It looks like this. And this way, you don't change the sequential execution or programming model. You have no changes to the virtual memory, because you're within a page and you can translate this instruction on the processor side when you execute in the processor. Yeah, minimal change to cache coherence. You will find that in the paper, but very small changes. And there's no need for data mapping in this case. Data mapping that's CPU-centric today stays exactly the same. And this is a huge limiter in terms of performance. But it's good for adoption. Basically, each PIM-enabled instruction operates on a cache block, which is guaranteed to be in a single DRAM module in existing systems. Nobody in their right mind today splits a cache block across different modules, because there's really no benefit you get out of that. I guess you could get some benefit, but bad idea in general. Yeah, you could. Okay, so this clearly fixes some of the issues. And then the question is, of course, who decides where this PIM-enabled instruction should be executed? It could be executed in the CPU. It could be executed on the memory side, right? And the idea is here to dynamically decide where to execute that PEI. Based on very simple locality detection. I'm not going to go through this in detail, but we have a simple hardware predictor that says, oh, the inputs to that instruction are in the cache. Let's say you cache, it's kind of like a cache hit predictor. Okay, that's the idea basically. So why would this provide any benefits? I'll go through this relatively quick. This is the same code that I showed you with it's a page rank based code for Tesseract. Now, if you want to update this next rank, in a processor-centric system, you need to bring this next rank to the host processor, update it, and write it back, right? So that's 128 bytes of data movement, assuming 64-byte cache lines. Now, if you actually ship it to the memory, this translates into a PIM instruction. You send the value to the main memory, and if your interface allows it, you send only 8 bytes, right? Interfaces are a different issue, but ideally, you send only 8 bytes. That sounds good. That's 16x reduction, right, in terms of memory bandwidth. And if there's no locality or little locality, this sounds great because you don't need caches anyway. Okay, that's the idea basically. So if you do this blindly, meaning if you always execute in memory, that's not a good idea. So we looked at a bunch of workloads. A lot of them are graph processing. As your graph grows, becomes bigger, doing it in memory makes a lot more sense because you get speed up by pushing these instructions to the memory side. If your graph is smaller, meaning if it fits your caches, then clearly doing it on the CPU is faster, right? So you lose performance compared to doing it on the CPU. Okay, well, I've kind of said this. Okay, so this is the idea of PIM-enabled instruction. I'm not going to go through this in detail, but these are some example instructions that we thought could be useful for different algorithms in different domains. Some of these are in-memory databases. For example, you have hash table probing, histogram bin indexing, Euclidean distance computation, dot product computation for machine learning. I guess I've said almost everything over here, but you can read more. But this was a study that to show that if you actually specifically target some instructions and some workloads, you can still get reasonable benefit without changing much in the system. Okay, I've already said a lot of these things actually. There's also, like, we also add this PIM fence instruction to make sure that a PIM operation completes when you get to a PIM fence, to make sure that these operations don't stay out on the PIM system indefinitely. If you know about multi-threaded programming, this is very similar to memory fence instruction. Okay, so that's an ordering instruction, which we're going to talk about. We're going to talk about ordering in the later part of the course. Actually, I had a question yesterday. Are we going to talk about like multiprocessors, etc.? Yes, but that's going to be pushed to the last third or last 40% of the course. So we're going to talk about memory ordering, cache coherence, etc., in more detail at that time. Okay, so the key to practicality here is really the single cache block restriction. Actually, similar restrictions exist in atomic instructions and today, because it turns out doing multi-cache block atomic updates is difficult in existing systems because you need to gather together and make sure that nobody else is updating those two or more cache blocks. When we talk about later, we may talk about transactional memory, for example. One idea in architecture has been, if I want to actually update multiple cache blocks concurrently, I start a transaction and then update everything that I need to update concurrently, and then I end the transaction. And the transactional memory abstraction guarantees that either the entire transaction executes or none of it executes. Meaning either you update everything you want to update or you update nothing. That way you actually can update multiple cache blocks, right? That's actually one way of doing processing in memory programming as well. So if you actually want to have a large region of memory to be updated using processing in memory, you could use this transaction abstraction and update multiple things. But okay, I'm getting ahead of myself. Okay, I'm going to skip this one. Okay, this is the design that we had. Basically, we have a PIM computation unit, a PEI computation unit, which is really integrated into the core. And then there's also a PEI management unit. And then these are, we again use 3D stacked memory here, but here our changes are very minimal. These are PIM computation units, PEI computation units that are actually specialized for special instructions, right? These are not in-order cores, complete cores. These are actually implementing specialized instructions. They could be reconfigurable also, I think, because this way you can imagine an instruction and you can implement it, right? Okay, so we evaluated using cycle level simulation. These are the workloads that we looked at the time. And this is the summary of the results. Basically, we see still reasonable speed up with large input data sets, 47%. The small input data sets is smaller, and energy reduction is significant. So I think these results are good, but clearly they're not like 13, 14x if you actually redesign the entire system. They're not even like 2x, right, when you actually offload a function. But we're not offloading functions over here. The downside over here is it's just instructions, right? So if instructions communicate with each other, you still have data movement between the processor and memory. Okay, I'll go through these relatively quickly, but large input sets. So this will show you the benefit of making a decision. Large input sets, if you actually always execute in memory, meaning don't make a decision, whenever you see a PIM-enabled instruction, ship it to memory, you still get a lot of benefit. But if you actually make a decision the way we did, you get a little bit more benefit. This is geometric mean. But there are some cases where our decision is not the best, as you can see over here, right? This may be actually breaking some of the locality in the instructions. So there's communication between instructions also, which this mechanism does not take into account. So whenever you're doing offloading, it's good to think about what benefit you would get by offloading, what data moment you would eliminate, and also what communication you may cause, right? So it's good to actually think about the bigger picture. So offloading a single instruction doesn't usually think about that. Offloading a chain of instructions that communicate with each other may make more sense. But then the computation unit on the memory side becomes more expensive. Okay, and this is the normalized amount of off-chip transfer. The interesting thing is here, these are small input data sets. Offloading small input data sets, as you can see, to memory is in general a bad idea, with some exception over here. I don't know why, I forgot. The paper explains it. This was published in 2015. So I think I can forget, right? It's 9 years old. If you've written a paper last year, don't forget. It will come up when people ask you questions about that paper. 9 years ago, it's fine. Okay, so basically, even in small input sets, if you actually do a locality-aware decision, you gain a little bit. Medium input sets are maybe the most interesting one, meaning these are input sets that kind of fit in the cache, not always, etc. So if you actually always offload to memory, that's a bad idea, as you can see. If you actually, in some workloads, well, maybe not a terrible idea, but actually you don't gain benefit. But if you actually selectively offload, then you actually start gaining benefit. So this also shows that it makes sense to think about mechanisms that actually offload. Like, how do you offload? What do you offload? These are actually important questions to answer. Even without data mapping being a problem, this is important, as you can see, right? Because here we eliminated data mapping. We just said data mapping is existing data mapping that we have. Okay, this is all energy consumption. And here you can see that the benefits are really coming from the large input sets. And medium input sets also have some benefit, but not as large as the large input sets over here. And we still get some benefit over here, as you can see, for small input sets. Okay, so essentially this is, as far as I know, perhaps the simplest and low-cost approach to PIM. It has no changes to the programming model, no changes to virtual memory, which are usually headaches, and very small changes to cache coherence that I didn't discuss, but they're very small, really. And it also dynamically decides where to execute an instruction. I think the huge disadvantage is really clearly it doesn't take into account the full potential of PIM. But again, it was not designed to take into account full potential of PIM because it was designed with adoption in mind. Okay, and I'll let you think about some of the other downsides potentially. I already mentioned some of the other downsides, like offloading on a per instruction basis without having the full picture of how instructions communicate may not be a good idea, right? Because communication may increase if you offload an instruction that communicates to another. Okay, I think this is a good place to take a 15-minute break. Okay, right on time. And we'll be back at 14:30 discussing more adoption issues. Taking out that. There's something flaky about it. I think maybe we should get another microphone here. Okay. Okay. It's time to get started. Okay, let's continue. So now you've seen one example of how to keep it simple. There are more examples, like how to ease programmability. I mentioned this yesterday. We're not going to talk about it today, but you could use compilation to decide what kernels or what warps in a GPU could be offloaded to near memory GPUs, simple near memory GPUs. And this is kind of the system that we looked at the time. If you actually automatically, meaning using compiler, decide what kernel should be offloaded. And then there's a dynamic component over here to make sure there's no resources are not over provisioned. You can get significant performance improvements without changing the software at all. I think there was an earlier question over here that I should cover. Here, there was a question that, like, how do you eliminate the virtual memory need? Like the translation itself and the access control checks, everything happen in the processor core. So when you decide to ship a PIM-enabled instruction to the memory side, you send the physical address, meaning it's the translation and access control checks and everything happen in the TLBs. If you need to do a page walk, etc., it all happens on the processor side. Okay, and the instruction gets sent to the memory only when the physical address is available. Okay, this eliminates the need for having virtual memory on the memory side. Okay, programmability. There's more on programmability that I'm not going to cover. I'm going to mention this later on a little bit. And I think of tools to decide what to execute where as programmability approaches also. They ease programmability. There's also more work. This is Nika's work that shows basically taking into account communication between instructions is important when you're offloading. Okay, let's talk about coherence a little bit. We'll talk a lot more about coherence when we get to the coherence lecture, so I'm going to offload a lot of the things over there. But this is an important issue also that this paper recognizes. And this paper also looks at basically offloading from the CPU to memory site or PIM site, again, 3D stacked PIM site, some portions of a program. And these are different programs like graph processing and in-memory database engines. And you can see that traditional coherence mechanisms sometimes even reduce performance. For example, if you actually use non-cacheable, if you don't cache the parts that are touched by the processing in memory instructions, if you don't cache that data, I guess I'm speaking outside. If you don't cache that data, then this is very bad for performance. But that's one way of ensuring coherence. Coarse-grained coherence means that you lock a large portion such that the CPU doesn't access it, or when it wants to access it, it needs to get that lock. Fine-grained coherence means it's very similar to existing coherence mechanisms. You expand that to the memory subsystem or main memory. And none of these are ideal, as you can see. If you ideally eliminate coherence overheads, you get significant performance benefits, as you can see over here. These don't look large, but these are smaller data sets because these are very long running workloads. And the solution in this paper, it's called lazy PIM, later renamed to Conda, actually gets a good fraction of the benefits, but not the perfect. It's not perfect, as you can see. So you need to do something smart about coherence if you actually are offloading a workload or partitioning a workload between processor and memory. Okay, it's good to think about that. We talked about some of this yesterday, like data mapping issues, and this also plays nicely. It plays into the data mapping issue also. You may actually need to replicate some data and ensure that PIM and the processor are working on different pieces of data most of the time, right? Okay, we'll get back to coherence later, but this is an issue that needs to be solved. Synchronization is another approach that another issue that we need to handle. I don't have time to talk about it, but there are papers. This is Christina's paper. Virtual memory is perhaps the hairiest issue. It's very hard to fix this problem, I think. Like, how do you How do you do the virtual address translation on the memory side without having a virtual memory infrastructure? It's expensive infrastructure. Usually what people assume is part of the memory is allocated to do computation on the memory side, and the translation is simple in that part. Right? That's one way of doing it, but it may not be the best way. So there's more work that needs to be done, except as you can see, there's not that much work in this topic. There's only one paper that's really specifically, or maybe more than one paper that really specifically looks at it. No recent papers that I know of. Do you know of something, Tarek? You look like you know, so. Okay. And then there's evaluation infrastructures that people need to develop for adoption, and there are some of these. I think at some point, Geraldo, well, I don't know when, but at some point in future lectures, Geraldo will talk about some of the programming issues and methodologies, etc. So you can see that there is a lot of issues over here. Let me talk about one programming framework very quickly. I don't want to spend a lot of time over here, but this is an example of the frameworks that I think we need to develop going into the future. This is really based on one architecture, which is the UpMem architecture we will discuss a little bit, but I think the concepts are generalizable, but the architecture needs to support the operations that are really assumed by the programming model, as you will see. So essentially, real PIM hardware is available, as we will see later, but programming is still challenging. You need to distribute data across memory banks, and each bank has a processor next to it. You need to manage data transfers between the host core and the PIM core, between PIM cores themselves, and between the DRAM bank and the PIM scratchpad. These are some UpMem specific issues, not all of them, but basically this PIM processor next to the DRAM bank has a scratchpad. It's kind of like a cache. So you need to move the data from the DRAM bank to the processor first in this particular incarnation of the architecture, which is probably not how I would really implement a PIM architecture, but that's how they implemented it for various reasons. One reason being they didn't really have access to the DRAM to begin with. They couldn't change the DRAM area that much. They needed to provide something that could plug into the DRAM, let's say macro over there. And then you need to launch PIM kernels on the PIM cores, synchronize properly between threads. So a programmer needs to think a lot about a lot of things essentially. So simple PIM, the idea is to simplify this. And the idea is to provide a high-level programming framework for real PIM hardware, inspired by other frameworks, like we provide iterators such as map and reduce. Clearly, this is similar to map reduce programming, and zip. And then communication mechanisms like broadcast, scatter, and gather. These are high-level. The programmer can write at the high level now, and these get translated into low-level code. There's a compilation support for it. That's the idea. Programmers should not deal with many things. That's the hope. And in this work, we have an implementation of it and evaluation with various workloads, as you can see over here. And it turns out you can get higher performance than hand-optimized code for 3 of the workloads, and you can get fewer lines of code for all of the workloads. So overall, it's probably a good approach, but I think this needs to be improved upon going forward also. Okay, I don't want to go through this in detail because Geraldo may talk about it, but essentially there's management interface for metadata management for different arrays that are in the processing and memory side, communication interface for multiple different communications, and processing interface, essentially to implement workloads. And I already mentioned that, high-level framework. Take the abstraction to a higher level so that the programmer's life is easier. It's in general a good idea. You don't want the programmer to worry about, at least you don't want the general programmer to worry about many things. Okay. And then if you actually have this high-level framework, you can implement, how do you get performance, of course? The performance is really allocated to the code optimizer, which is really a dynamic or static or dynamic compiler, right? And these are the code optimizations that are implemented based on the high-level framework. And you can find more information in the paper. So there's more in the paper, but for example, just to give you an idea, this is the hand-optimized program for histogram with UpMem software development kit. You can see that it's C-based. And this is the simple PIM histogram. So it doesn't really need to deal with a lot of things. Simple PIM histogram is much simpler over here. So you can see there's a create handle and then scatter and a reduction operations. Okay. And these are the lines of code of different kernels, let's say. Okay, and this is a performance evaluation, which I kind of mentioned. Okay, sounds interesting. I think these are the sort of things that we need to deal with. But I mean, we need to deal with everything, of course, across the stack. But programming is really important. High level is really important. Okay. So, and then, of course, there are applications to show. This is one of the things that we have been doing in research. Like, if you remember my adoption issues, what kind of applications would benefit, right? What kind of software would benefit? So it's good to have case studies of different types of algorithms and different types of approaches that would benefit from different types of PIM, in this case, near data processing, but also for processing using memory as well. So that's why we looked at GPU execution, and there are other papers also. I'm not going to talk about any of these, but in one of the works, we designed accelerators for linked data structures. So if you have a linked data structure, for example, a linked list, this is a very latency bound operation. So bringing everything to the CPU and then doing the addressing and then going back and bringing the next node to the CPU and doing this over and over is basically puts the pointer chasing on the critical path, right? And these pointer chasing applications, you can reduce the critical path by doing the pointer chasing on the memory side, right? That's the idea over here. Then the question is, how do you design the accelerator? There's also more work to transparently accelerate dependent cache misses. This is accelerating my own PhD thesis. In my opinion, this is the right way of doing run-ahead execution. But when we talk about run-ahead execution, we'll talk about that. Essentially doing run-ahead execution on the memory controller. We've looked at using FPGAs with high bandwidth memory to accelerate different types of computation, in this case, stencil computation. We will probably talk about some of these works when we talk about genomics. But this is one of the early works in genomics. And I like this work because it actually has a high level of rethinking of how we should represent the genome so that it matches the parallelism and the characteristics of memory. The idea here is to do some filtering of the genome analysis on the memory side, but to be able to do that, it really has a new representation of the reference genome, which you will read if you actually which you will find if you actually read the paper, so that it fits nicely to the hardware. And I like this approach a lot. And then there's more work that accelerates approximate string matching near memory, accelerates other algorithms like sequence to graph mapping, and more recently, other things that I'm not going to talk about. Time series analysis is actually a very important application, I think, and there's work that we've done in this area that you can take a look at. And we've already talked about graph pattern mining a little bit. Database, so databases are actually applications that were used in the early 70s to also say, oh, okay, we should really do processing near data because these databases are doing a lot of operations that are data intensive. And more recently, people have been developing hybrid transactional analytical databases. Here, the database is partitioned into two types of threads. One are analytical threads. Essentially, they do analysis, and the others are transactional threads. You can think of analytical threads as threads that actually search for some data. For example, the bitmap operations that we've seen. I want to find all the people in this room who live somewhere, I don't know, Zurich, let's say, and who are older than 25, and I don't know, who like trees. So you can actually, that's an analytical query that you can actually send to a database. You really do a lot of scanning of the database to be able to answer that question. If it's represented with bitmaps, you scan the bitmaps. If it's represented by B plus trees, you scan the B plus trees, etc. Whatever data structure you use. So that turns out to be very streaming and very data intensive. And then there's a transactional queries that basically says, for example, I want to update this location in the database. That's transactional. That's not analytical. You're not searching things. You really know what you're going to update. For example, you want to create a new entry in that database because there's a new person joining this room, right? That's transactional. And these transactional analytical queries have different requirements. Transactional queries usually are not as data intensive as analytical queries. So it makes sense to partition things such that analytical queries and transactional queries are executed in different ways. And database people actually figure that out. So they have these hybrid transactional analytical databases. In this work, we actually have customized acceleration for especially the analytical part. If you're interested, you can actually talk to Geraldo. This is Amirali's work, but Amirali worked with Geraldo on this topic. Okay, ML inference we already talked about, and other data intensive workloads we also talked about. Maybe I'll talk about this work a little bit when we talk about processing, real processing in memory engines. But that's the reason why I think we need to look at more workloads. And if there are other workloads that are interesting, people should look at them. And clearly this is our work, but there's a lot of other work also that I cannot fit in all of these slides that talk about other workloads. But you may see some of those in the reading lists that we may put. Okay, so I think the adoption issues require us to visit the entire stack as well. Any questions? I'm going to put something just so that you can maybe start thinking about it. And then I'm going to switch to more real processing in memory architectures in the remaining time. And let's see if we have time for robustness. Okay, so this is something that we have been thinking of for some time. I think this is an important direction. And this is the interaction of processing in memory and security. It's good to think about this, I think. We, for example, earlier in the lecture, the previous lecture, we've talked about generating random numbers or generating physical unclonable functions. I'm giving you the example of doing remote attestation using this physical unclonable function. If you actually do those things in PIM, you can create a security infrastructure on the processing in memory side. And this could make security better or easier, right? Because you could actually, you're reducing the data movement. And if security critical functions actually execute on the processing in memory side or memory side or the storage side, that means that data moves less, which means that it's less vulnerable to inspection. I think in general, one of the problems with side channels and information leakage is data moves a lot or things move a lot and they become vulnerable to inspection if they move a lot. So I think fundamentally moving data less actually can make security better. But of course, this requires building the security infrastructure on the places where that security critical data is processed. Then the question is, of course, can PIM make security worse also? And I think there's a paper that Nisa and Konstantinos has led that looks at timing and covert channels being worse with processing in memory operations, right? I think Konstantinos is busy with virtual memory right now. Okay, I think there are many interesting questions here to look at. So if you're actually doing operations on the memory side, you could accelerate some of the information leakage also. It's good to think about that. And then there's other stuff, other things that you can actually make more easily on the processing in memory side, like homomorphic operations. If you have homomorphic encryption, this is an encryption technique that's extremely high cost today. But if you actually do it on the memory side, maybe you can reduce some of the cost of it. And this sort of thing actually needs to be examined also, because if you really want to be secure on the memory side, maybe you need to encrypt the data as much as possible and maybe operate on data that's encrypted as opposed to trying to decrypt the data and operate on it and write it back. And homomorphic encryption is an encryption technique where people have developed mechanisms to operate on the data that's encrypted. Again, this is to give you a broad picture as opposed to going into each of these mechanisms, because each of these mechanisms require their own individual lecture to talk about, like how to do homomorphic encryption, for example. But you can read and find out more. Okay, so there are papers. Okay, I actually gave a talk on this topic also. Okay, if there are no questions, let's jump into the last part, which is the kind of small survey of processing in memory in the real world. This part didn't exist when I was giving the lectures until 2020 or so. And it started creeping in. Right now we could actually have full lectures on this topic. So this tells you that things are happening. Okay, so you can find a lot more information in our PIM tutorials. In fact, there's an upcoming one. This is all open source, meaning all online. You can join with the YouTube link, you can contribute, etc. And there are previous versions you can also watch. So in these tutorials, initially these started as real world processing in memory tutorials, meaning we wanted to look at these real world PIM systems, and we invited people from industry to talk about what they built, etc. So you can find some of the older ones. And then more recently, we're actually broader, meaning it's not just real, but it's also future processing in memory systems. So, but there was a lot of interest in all of these conferences, large attendance, and people participating a lot in these tutorials. So this also shows the interest in the community. Clearly, you can see also interest in published papers. I think the upcoming micro conference, which is one of the major computer architecture conferences, I think it has three or four sessions on processing in memory. I don't know if that's at least 3. And then there may be other papers on processing in memory around in the other sessions that are not classified into that particular session. Okay. Okay, so one of the things that you can do in real systems today is using FPGAs with high bandwidth memory to accelerate applications. This is a form of processing near memory. Maybe poor man's processing near memory or something like that, because it's basically taking advantage of the FPGA near memory to offload computation from a CPU to the FPGA. Right? You can think of it that way. And that's the idea. In this work, we worked with IBM to do something like that. Essentially, IBM has been implementing these flexible interfaces like OCAPI for a long time. CXL, Compute Express Link, the flexible interface we talked about very briefly, is somewhat similar to OCAPI actually. It's not that different. Maybe some specifications, some little things are different, but at a high level, these are very similar interfaces. It's a cache coherent interface that enables offloading computation to somewhere else other than the CPU in a flexible manner. And if you can do that now, you can offload computation to the FPGA in a flexible manner, and it could be cache coherent, etc. But in this particular work, we wanted to understand what to offload, and we focused on two workloads, like climate modeling, specifically the Cosmo workload, and genome analysis, specifically some pre-alignment filtering mechanism that you will learn about later on. And we looked at multiple different interfaces like DDR4 and HBM, and also different interconnect technologies, but don't worry about that right now. But the idea is, if you can offload some functions over here, data-intensive functions, you can accelerate them in two ways. One is you have access to very high memory bandwidth because you have HBM over here, right? And also you can customize the hardware to the function, right? Because of the FPGA reconfigurability. Clearly, it's not perfect customization because programmable reconfigurability, right? So there's overheads in FPGAs in general compared to an ASIC or a fixed function accelerator, but it's still better than what you can do in a CPU. In a CPU today, we have a lot of control overhead, right? You need to fetch the instruction, decode the instruction, and do a lot of bookkeeping. Execution is a very small fraction of the energy and performance. You do a lot of other bookkeeping stuff to actually execute something. Whereas in an FPGA, you can program the circuit so that execution is the biggest, hopefully, the biggest, and you don't have the control overhead as much. In ASIC, you get rid of all of the control overheads, almost all of the control overheads. So it's good to think about that. In general purpose systems, you have a lot of control overheads. So here, we get rid of a lot of that. Okay, so again, without going into a lot of detail, we will cover, I think, one portion of it in the genomics lectures, hopefully, but you can see the benefits that you get, even with this existing hardware on some kernels. So we get significant performance, energy efficiency compared to a pretty powerful IBM Power 9 CPU at the time. And you get both of them at the same time, basically. Performance and energy efficiency both improve. That sounds good, right? Yes?
So the FPGA uses an HBM, and HBM is going to have lesser density.
That's correct, yes. Mm-hmm. Yes.
You want to do chem, so you want to do as much computation there. You need that capacity there.
So in this case, we offload things like that, we don't exceed the capacity. Right. Yes, but you're right. If you want to really, if you really have a very large part of the workload that you want to offload, then HBM unfortunately doesn't satisfy the capacity. That's why you need to build something like Tesseract, right? Network of HBMs or network of FPGAs with HBMs. You could also do that to offload the workload.
So the modeling and the genome analysis workloads considered, or is it not big enough?
So in this particular case, we offloaded specific functions. So if you read the work, you will see that it's not the end-to-end everything in the workload. So some of the workload executes on the CPU side still. So it's not perfect. But this is essentially, I think what you're getting at is very fundamental. If you have small memory, you will need to think about the scaling approach to the system, right? So FPGAs, using multiple FPGAs with HBMs, a network of that is one approach. Very similar to what GPUs are doing today, right? You have GPU, HBM, and then you have a network of GPU and GPU plus HBM today. It is scalable. It's expensive though, but it's not scalable enough. Yes, I agree with you. I agree. Depends on what you mean by scalable. Yeah, I mean you can scale anything, but then performance at some point may suffer because you need to communicate between these units, right? Okay. Okay. So this is the UpMem processing in DRAM engine, which was introduced in 2019. Essentially, this is the first commercial processing in memory chip. It looks like a standard DIMM, standard module essentially. But each of the chips, DRAM chips in a module, have processors in each bank. Okay, which is very interesting, clearly, because these processors have access to the bank almost directly. But we will see that. And you can see that there are many DPUs. They call DRAM processing units. They operate at very low frequencies. And the reason is they're implementing this on a DRAM process. And DRAM process is really optimized for a different fabrication goal. So everything is different in fabricating DRAM compared to a CPU logic. It's really optimized for capacitor. You need to really make the capacitor small, etc. And as a result, if you want to put logic in it, and if you want to operate at very high frequencies, this becomes extremely leaky. Or you need to actually put a lot of huge buffers, etc. So they operate at only 350 megahertz. So comparison point is 4 gigahertz or so today CPUs, right? So immediately you're bottlenecked by frequency, as you can see, near the memory side. But even then, you can get some benefits. So this is what the system looks like. This is a real version. Unfortunately, they made the decision that there is main memory in the system, but then there's also PIM-enabled memory. Meaning, if you want to process the data, you need to move the data from main memory to a PIM-enabled memory. I think this was a not so great design decision. They wanted to treat PIM as another device in the system, just like a GPU would. Normally, when you want to start execution on a GPU, you move data from main memory to the GPU memory, right? They kind of wanted to preserve the same thing, but I think hopefully they'll change this design decision, because this causes additional data movement to start your application, right? But ignoring that, I think it's a very interesting system study. And this is, we gave a lot of talks, Juan gave a lot of talks on this topic, but this is what the processor looks like. So each DRAM chip has, I think, 16 banks over here, and each bank has 64 megabytes of DRAM. And then this is the processor over here. It's a multi-threaded processor, multiple instruction, multiple data, fine-grained multi-threading, meaning every cycle you fetch from a different thread. And the reason they did this, I believe, is because they didn't want to complicate the pipeline with data dependency checking and branch prediction logic. If every cycle you fetch from a different thread, you don't need any of that control overhead, which means that your processor is much simpler. And then you can see that there's an instruction memory, and then there's a data memory, scratchpad, WRAM, and then there's a DMA engine to get the data from the DRAM bank to the instruction memory. So this is very, very classical processor, as you can see. It doesn't even have direct access to the DRAM bank, as you can see. It needs to operate on data brought into the, I'll call them caches, software managed caches, right? So in that sense, there are a lot of overhead still internally, but even then, some workloads benefit a lot if you offload them. There's also, if you want to, for example, communicate between an operation that's done over here to another bank, there's no way to do that internally inside the DRAM chip, even though those banks are in the same DRAM chip. Unfortunately, they didn't modify the interconnect architecture to do that. And there are various reasons why this is costly, because one reason is the memory mindset, right? When you design memory, there's really no need for a lot of interconnects to communicate between different banks, because the memory mindset says, I access one bank, I get my data out and put it out. It's not designed with the thinking that I access one bank, I get the data out and ship it to some other bank, right? There's no easy communication across those banks, at least the way they would like to do it over here. There's some shared bus, as we discussed last time, but they're not doing it that way. They're not using that shared bus, unfortunately. They're doing computation, and they need to modify some mechanisms, but they were not able to touch that part, DRAM core, if you will. So if you change memory to do computation, maybe you should also think about changing the interconnect on the memory side. But that's not what's done. Even then, I think there are a lot of workloads that benefit. That's the good part. Even with a lot of these limitations of an existing system, I will show you a lot of workloads benefit, and there are a lot of works that show that a lot of workloads benefit. This is a paper that we wrote on this topic. You can take a look. It's a very long paper, but it covers a lot of things in detail. And Juan gave a lot of talks on this topic. But let me give you some key takeaways over here, so based on our experimentation. Basically, this PIM architecture is fundamentally very compute bound. It's very low frequency. Its operations are in general, relatively simple. So they don't have anything more complicated than an 8-bit integer multiply. So there's no floating point. There's nothing that's more complicated than what I just said. So basically, the performance saturates at very low arithmetic intensity, as you can see over here. So the most suitable workloads are workloads that are very, very low arithmetic intensity, as you can see. Okay, that's one thing. And also, if you have no arithmetic operations, or if you use only simple operations like integer addition, subtraction, bitwise operations, then these are much better suitable because other things are not supported, right? If you want to do floating point, good luck. The way they do floating point is essentially virtualization. Basically, there's some program that runs, and it really emulates, emulation I should say, it really emulates floating point, for example, or fixed point, etc. Even then, there are some workloads that benefit a lot, as you can see over here. These are some comparisons to CPU, GPU. Well, CPU, GPU are the baselines. And then you can actually have, in this system, you have, there are multiple systems. One of them has more than 2,500 DRAM processing units. And you can see that some workloads like scanning benefits a lot, on par with GPUs, as you can see. Some workloads like histogram is better than GPUs. Some other workloads are also better than GPUs. But then some other workloads are pretty bad compared to GPUs for various reasons. One of them could be there's no good multiplication unit, for example, in this case. A sparse matrix vector multiplication is pretty bad, for example, as you can see, etc. Okay. Okay, so the other key takeaway from this workload analysis is really if workloads are doing a lot of communication across bank or requiring a lot of communication across banks. So if you want to do a reduction across banks, for example, or some synchronization across banks, it doesn't fit this architecture very well because that communication is done through the CPU or host CPU. So you actually have additional data movement to do synchronization. That's because it's not supported in this current system. Okay, so those workloads don't fit. But even then you can see there are significant benefits. So that's the upside, even with all these limitations. So there's more papers that we've written on this topic. And these benchmarks are online. You can use it yourself. Actually, you will have a programming assignment where you program benchmarks on UpMem system. You will see some of these idiosyncrasies yourself. And maybe you'll get performance, who knows? Okay, and other people have used it. Other people have used it for other purposes, actually. I've seen papers that have used prim benchmarks for evaluation of other processing in memory systems than UpMem as well. Okay, so there's a lot of information. We've also looked at doing machine learning training for classical machine learning models on this UpMem system. Again, you need to work hard as a programmer to make this work at high performance. Essentially, you need to optimize data representation so that you don't do complicated operations. You need to reduce the data precision, and you need to use hybrid precision. As much as possible, use lookup tables to implement complex operations, and optimize the data placement and layout for streaming. If you do all of that, so with some programming effort, you can beat the CPUs and GPUs, which is good. So there's, as you can see, having a real processing in memory system enables you to experiment with real workloads in a nice way. So it's good that people are producing real hardware. And you can find information in these papers. Christina did a lot of work in his thesis or her thesis to actually get sparse matrix vector multiplication work nicely as much as possible on the UpMem system. She didn't quite succeed, but she worked very hard. She looked at many different things. Meaning many different ways of doing compression, data types, data partitioning, synchronization, and load balancing, so that she could get good performance out of a sparse matrix vector multiplication, which is really the core of a lot of machine learning algorithms today, clearly. But unfortunately, it doesn't work really well on this system because the system really cannot support multiplication in a reasonable way. If you really want to be able to do that, at least you should have the multiplication primitive. Even if you have all of the other downsides, not having multiplication nicely hurts. Do you agree? Okay. Okay, but you can download this and improve it on yourself. Improve it by yourself if you want. Okay. So there's more work that I'm not going to talk about, but this was Morris's. I think it was his master's thesis, right? Yeah, it was a master's thesis that looked at implementing transcendental functions, which are actually complicated functions on the UpMem system. And I think he did a great job having a library that actually implemented this. This is also a tough workload. But one thing that works really well is actually sequence alignment. This is where, because sequence alignment is composed of operations that it basically fits those takeaways really nicely. you have very simple operations in general. You don't need multiplication for sequence alignment. You can do a lot of bitwise operations. And if you optimize the algorithm, actually, you can actually reduce the strength of the operations even more. You don't need a lot of communication because you can do a lot of things in parallel across banks. And you can exploit parallelism so that you can cover up for the low frequency, for example, right? And in this work, we actually looked at a lot of sequence alignment algorithms, like Needleman-Wunsch. WFA is one of the latest algorithms in this area. So there's still algorithmic improvement that's happening. And we basically found out that you can get substantial speedups over both CPUs and GPUs. Again, I think the speedups could increase with better algorithmic approaches, but this is showing that real alignment algorithms benefit from even this sort of architecture because the alignment algorithms don't tend to require complex operations. No, not at all. This is all integer and very relatively simple. In fact, for example, in the GenASM work, maybe we'll get to it, but it's a lot of bitwise operations. The reason we designed the GenASM algorithm based on some earlier algorithms was to make sure it's capable of doing things in a bitwise manner so that we could fit it to memory. And yeah. Okay. You will see that when we talk about genomics. Okay, so there's work Harshita and Mayank did on homomorphic operations. When you have multiplication, it doesn't work. When you have addition, it works. It doesn't work, meaning it doesn't perform well, basically. So anything that requires complex multiplication is not good on a system that doesn't have a good multiplier. That makes sense, right? Hopefully. Okay, we've been also looking at accelerating reinforcement learning. I will not go through these in detail. These are more recent papers, but I think these are very interesting things to examine in real systems. And we have a paper coming up. This was Steve's bachelor's thesis. He's going to present at PACT, I guess by the end of this month, right? He worked pretty hard to actually to get stochastic gradient descent working on the UpMem system. Again, you can read the paper for more details. But in the end, I think this requires better support from the hardware. Okay, there are some conclusions. And then we have another work coming up soon on accelerating graph neural networks. This is again Christina's work, as you can see. Okay, I'm going to skip these because you can talk more about this. And then there's other works actually in this area. There was one work from SNU that in Korea that looks at benchmarking and understanding the UpMem system, and it won the best paper award at HPCA this year. It's a good paper, and they also have open sourced a lot of their simulation infrastructure to experiment. So, and then there are also other works that look at accelerating databases on UpMem, and I think they show good results as well. Because again, a lot of the database operations do not require multiplication or floating point, right? Okay. So there are other prototypes, other real processing in memory systems that are not as open to public. With UpMem system, if you have money, they'd be happy to take your money and you can buy the system and you can experiment. You can do whatever you want. You can do Bitcoin, whatever, yourself if you want. I don't know if people still do that. But basically, that's a commercial system. Anybody can buy as long as I guess they talk to UpMem. But these are some systems that are developed and prototyped, and papers have been written about these systems. But as far as I know, people are not buying them. But maybe some companies are experimenting with them. Who knows, right? That happens in general. Actually, they are experimenting with them, I know. But this is Samsung's system that we briefly talked about. They used HBM2, and they basically added simple computation capability near each bank. And you can see the specifications over here. I will not go through everything over here, but funny, they used the PIM computation units, which we used earlier with PIM-enabled instructions. But you can do now floating point addition, right? And multiplication, and multiply and accumulate, and multiply add. This is what you need for machine learning workloads. Although machine learning workloads may be trying to get away from this also, as we discussed yesterday. So basically, this is an accelerator that can accelerate these operations. It's not general purpose. If you have these operations, you can offload them. And I think basically they have an example over here. They have some registers, etc. Yeah, you can read. Basically, it's an accelerator. And this is kind of the instruction set for this accelerator. So you can do some sort of branching and a limited set of operations, as you can see over here. If you can offload a good chunk of your machine learning kernel, you get benefits. And that's what their papers show. But I'm not sure if it's independently validated yet. It's good to think about that. Okay, so they have a real chip, basically. which is good. I think a major manufacturer is doing things like that, right? And then there's also this thing that I will very briefly mention. These are things that you can build without modifying the DRAM chip. So it's a little bit different. Essentially, you have a lot of DRAM chips on this board, and then you have a buffer chip. And this buffer chip is connected to all of these chips. And this buffer chip can get data from all of these chips and do some processing, and then write data back or send the data to the host, etc. And Samsung and Meta, I think, designed this so that they could accelerate recommendation systems, recommendation inference in real workloads. I don't know if this is being used in real systems, but they wrote papers about it and showing that they get good benefit. And then SK Hynix's chip is actually more similar to the Samsung's earlier chip, where they actually use a GDDR6 chip to actually do computation. And computation capabilities seem very similar to what Samsung has. It's basically accelerating floating point multiplication and accumulation, etc. And they actually gave one of the talks at one of our tutorials. I think this is at S+ 2023, as you can see over here. It's a good talk. If people are interested in learning more about their system and software stack, you can take a look. And also, Alibaba has also another chip, and you can see some information about that. I'm not going to go through this. So the good thing is, as you can see, there are a lot of DRAM chips right now that are around. Maybe you cannot get your hands on it, but people are writing papers about it. People are doing performance evaluation with it. Some people are evaluating it, etc. And then there are other papers that I mentioned that are enabled by CXL. This is very similar to, in my opinion, to the work that I mentioned that we did with IBM. Right? With IBM, we offloaded using the OCAPI protocol to an FPGA that is HBM. This is essentially another FPGA, and I believe this is HBM also, but I don't remember right now, so don't quote me on it. But it's an FPGA that's near memory. They looked at some other applications, I think more database type of applications in this particular case. Okay, Samsung did something, but it's very hard to decipher what they did sometimes. So you can go to some of these talks and understand what I mean. Okay, any questions? And then there are a lot of other experimental chips and startups that are doing things, but I don't want to really discuss them at this point. You may find out about them. If there are no questions, I'm going to conclude the memory-centric computing part, and then we can take a break. Did you have a question? No, okay. I thought you were raising your hand. Maybe speculatively raising your hand. Okay, let me conclude. So I think this was to give an overview of memory-centric computing. We'll have more detailed lectures later on, and we'll also have the more detailed lectures on DRAM. But I think the key is we want energy-efficient architectures, and I believe they need to be data-centric. And we want high-performance architectures, and I believe they need to be data-centric also. And we want more robust and secure architectures, and I also believe that they need to be data-centric. Fundamentally, we want to minimize data movement for all of those. Well, that's what I said. Now let me give you the fun part, and then we're going to take a break. I used to start my lectures with this fun part, but it actually fits this nicely as well. So some very famous architects said architecture should be based upon principle and not upon precedent. Can anybody guess who said this? Nobody knows famous architects? Who? Okay, that's a good guess, but no. Older? Not that old? Well, okay, maybe I'll give you a hint. This guy is an ETH alumnus. No, not this guy, sorry. That's the other architect that we're getting. This guy is an American. It doesn't fit either of those. Maybe he's the most famous American architect. Nobody? No Americans here? Come on, I'm going to spot some American over here, but I cannot. Okay. It's okay. Does this help? No? Who has traveled to US over here? Okay. Who's traveled to New York? Okay. Who's been to the Oculus? No one? This is the station on Chambers Street, very close to the World Trade Center. No? Maybe. Okay. You'll see a picture of it. Okay. This guy is Frank Lloyd Wright. Maybe that name means something, but hopefully it will. But Frank Lloyd Wright was a famous architect, and he really believed in principle. And I actually agree with him on this, at least this particular quote. Basically, we've been designing precedent-based architectures for a long time. I think it's good to really design things from blank slate with principles, as opposed to being, let's say, slave of precedents, because that's how things have been evolving, I think, in computing system design today. Or at least the slave of precedents. Oh, we really tweak the system to make things work, but there's a huge inefficiency that everybody ignores. There's a huge cost that everybody ignores. And hopefully I've pointed out to some of that cost. And this cost is also in terms of sustainability. We're building these chips. Maybe we can build chips that are much simpler if we actually do the right thing in the system level and do the computation somewhere. Okay, but this guy could have designed something like this, which could have been precedent-based. It's not a bad place, actually. But he didn't design that. He designed something like this. This is a more principled architecture according to him. How many people know this place? Okay, you know what it is? Yes, falling water, exactly. Say it again? You have a Lego model of this. Okay, yeah. Now you know the architect also. Okay. Yeah. I mean, this used to be very close to where I lived in Pittsburgh. I was a professor at Carnegie Mellon University, and this is a place I would go for inspiration. And whenever you go over there, it gives you a lot of inspiration, actually. I would recommend my students to go there also. And they should, I think. I think people should really go to these inspirational places as opposed to boring places. But basically, this is based on precedent, and it's also expensive. This is cheap. This is expensive. New technology is always expensive. A new model is always expensive. But you can amortize the cost over time, right? You can move there with large cost, but over time, the cost gets amortized. That's the thing that people don't think today in general. We have huge cost. Yes, a huge modification to that hugely cost system is expensive, but that's a one-time cost you pay, and over time, you amortize the cost. Then the cost over here is amortized because they charge you a lot of bucks to enter. So I bet this is amortized, I guarantee you. So it's based on some principle, as you can see, organic architecture. I'm not going to read this. This is another example of precedent-based design. This is a run-of-the-mill train station all over Europe, but Germany in particular, boring. Trains are probably pretty late, or they don't arrive, so they will leave you there. That happened to me multiple times, so I'm speaking based on experience. And this is a more principled design. Hopefully some people know where this is. No? Stadelhofen, exactly, yes. Well, yeah, Stadelhofen. And this is another principled design from the same architect. Do people know where this is? I guess there's a lot of side channels here, so you got to not look at the lower part. It's in Portugal. It's the Garde Oriente, and this is the principle. The kind of zoomorphic forms, right? Whatever those are, gods. Greek gods, I know. What is the name of this, Konstantinos? Okay, I don't think it's a Greek god. He couldn't figure it out. That it must not be a Greek god then. Okay. And this is in Valencia. And then this is Oculus. Whoever went to New York. Next time you go to New York, you got to go there. And this was costly. New Yorkers at some point told this guy, we're not paying you anymore. So the transition to a new paradigm is always costly. Now, who's this? This is the ETH alumnus. Yes, Calatrava, exactly. I'm glad one of you got it. Otherwise, it would be kind of embarrassing. Maybe ETH is not really good at promoting their alumni, and that's true. I think you need to be more nicer to your people. It's yeah. Okay, this is Calatrava. Well, I don't have the name over there, but essentially, my point is these are principled architectures, and there's a principle over here. And whenever you move from the business as usual to something more principled, then you actually need to pay at least some large one-time cost. But this should not be a good reason to not move, right? Because if we had not moved, if we had not let this guy spend a lot of money to build this thing, then you would not experience that thing, right? Nobody is going to go to a random station and take pictures. Now, if you go over there, you'll see lots of people taking pictures. Now, I'm not sure if actually this amortize its cost, but there's some value to it that could not be quantified, perhaps. Right? When I visited Beijing, actually, one of the recent times, in Beijing, the Summer Olympics was held in 2008, and they have this bird's nest that they built. Does anybody know what I'm talking about? This is a huge Olympic stadium, right? You've been there? Okay. You were there that summer? No, oh, this summer you was, okay, yeah, that's good. Yeah, I should use that also as an example. I think they got it built by some Swiss architects, Herzog and someone, but yeah. And they paid a lot of money, clearly. But they told me that, and of course, I'm relating their view. They basically said that it amortized its cost over the 15 years or so. So that new technology amortized its cost. It's good to think about what is the right thing to do as opposed to what is the easy thing to do, or what can I make more money in at least immediately. Because if the only thing you're thinking about is what am I going to make money in immediately, then there's no future. Then there may be really no future for anyone, right? Okay, so the other thing that I would like to mention is I think there are principles that some people follow clearly in these architectures, but are there principles for computing also? What are the overarching principles for computing? What is the thing that we should say how we design? This is how we should really design our computing systems. I certainly don't believe that this is a processor-centric principle. Like memory here, CPU here, storage here, communication separate. Maybe that's part of the bigger set of principles, but this should not be the overarching principle in my opinion. And if you look at some compute engine, I believe this is some sort of compute engine, your brain. And clearly we don't understand enough about it, and clearly I don't understand enough about it. But at least based on what I understand, this doesn't have that processor-centric principle. It's more of a distributed system where communication, computation, and storage happens in a more meshed way. Okay, it's good to think about that. Okay, so I think I've covered everything, but I believe there's also another principle, I think, that we're violating immediately. If you've taken DDCA from me, I said that a computer architecture should be balanced, right? That's the key design, one of the key design principles. Balance means there should be no single bottleneck. When data flows or when a workload executes, one thing should not dominate execution time or energy or whatever metric you're caring about. Unfortunately, I teach that, and then immediately I go and teach a processor-centric design, and I violate my own principle of communicating principles, right? Basically, it's kind of a shame that we preach and then we do exactly the opposite of what we preach. Our designs are completely imbalanced today. And hopefully you've seen a lot of evidence in this lecture. And as a result, they're not high performance. As a result, they're not energy efficient. And if you want to make them more balanced, high performance, energy efficient, we need to be more memory centric. And hopefully I've shown you that this can enable lots of improvements in many metrics. I believe it can enable new applications and computing platforms. And I also believe it can actually enable a better understanding of nature, which we really don't have a good grasp of. For example, when I was an undergrad, I majored in computer engineering and also psychology. It's funny to major in both, I think, because psychologists always wanted to use computer science as a paradigm to understand humans. Meaning, in these lectures, you would say, oh, computer science or computers are a way of, computers can give us some insight on how humans operate because the operational principle of computers resemble humans. I think hopefully they dropped all of that from the textbooks. And I think they dropped that over time. They realized that these computers are not, maybe at least the existing computers are not like that. So I think if we actually build computers that are more aligned with nature, we can understand the nature much better, right? I think this was the premise of neuromorphic computing, but neuromorphic computing, unfortunately, in my opinion, didn't really progress as it should have progressed a lot more. I think it had a lot of potential when it started, but progressed a little bit less than expected. I think it needs to be more general purpose, basically, I think, to progress more. Okay, who knows what else, right? So I think the future of truly memory-centric computing is very bright, but we really need to do the research and design across the computing stack. Okay, I think I'm going to stop here. I should also say that there are a lot of people who are interested in it. We get a lot of funding from a lot of companies at various times to actually support memory-centric computing, because even though they may not be immediately building it, they really want to understand what could be built. Or what could they build at that point, at some point in time? Or if it comes at some point in time, how should they react, for example? So they're quite interested in donating funding. And if you're part of a company, feel free to donate more funding. We're always happy to. It goes for a good purpose. So some people do great PhDs, right? That's the goal of the donating funding. We don't waste it like some other institutions do. Okay, I'm going to stop here and I'm going to check the time and I'm going to be afraid maybe. Oh, okay. I think we can still take a 15-minute break and continue with the memory robustness. I want to get a start on it so that we can continue next time. Let's be back at 15:40, assuming this is correct. Okay. Let's get started. In the last 20 minutes, I'll make an introduction to memory robustness, and then we'll continue next Thursday. Any questions on memory-centric computing before we start? We will have more depth, and you'll read some papers. So hopefully it's going to be exciting. How many people think this is exciting on memory-centric computing? Okay, I see some hands. That's good. That's good. Okay, let's talk about memory robustness. I think this is another critical topic that we may go deeper on. It's a broader area because it really affects infrastructure. And this is an example infrastructure that people built. It's a bridge. And once a bit flip happens to a bridge, this is what happens. It becomes a security, safety, reliability problem, essentially. And these bit flips happen, even though people have been building bridges for a long time, right? And this is another example that I like using. These guys are sitting on this rod. And if they have a bit flip over there, they may not be very happy immediately, right? And then you've seen some of these pictures where we show tongue-in-cheek other infrastructures that self-drive for you. And it's good to, I think, raise the bar for robustness in those infrastructures where we bet our lives on, perhaps. And then there may be other infrastructure that we use to go to space, for example, like safety critical infrastructures and infrastructures that deal with the unknown most of the time, right? A lot of these are infrastructures that deal with, well, I guess there's an unknown component over here in driving, right? But some of these are known, but there will be a lot of unknowns, a lot more unknowns, basically, as computing infrastructure expands to many things in life, right? So we're going to talk about RowHammer. So RowHammer is the fact that you can predictably induce bit flips in computing infrastructure, in commodity DRAM chips. And essentially, all recent DRAM chips are fundamentally vulnerable. And this is one of the things that makes the security problem is it's really, as far as I know, the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. People have looked for this reliability security connection, but it was more or less theoretical for a long time. And RowHammer changed that. It made it more practical, essentially. So essentially, now you can actually cause bit flips from software directly. And people are writing articles that look like this. Forget software, now hackers are exploiting physics, which is interesting. I'm going to give you a little bit of history before we go into the details. So probably we will end with the history by the end of this lecture, since we don't have a lot of time. But we've been looking at memory for a long time, and we've been writing papers about it. This is one of the papers I present at the International Memory Workshop, which is an industry-dominated workshop where industry presents a lot of the memory advances, etc. And we've always argued that technology scaling will not go well. We should really think of memory differently and take a more system architecture perspective. And this includes looking at reliability issues and solving them from a systems perspective, and also thinking of memory as not just a storage device, but also as a computational device. So we actually argued a lot in this paper. And our goal was to actually ensure that scaling continues in a better way. So if the technology doesn't scale, maybe the system will scale by overcoming the deficiencies of the technology. This is kind of similar to what things have been happening in architecture, right? If you think about it, if you don't get benefits from each transistor is not scaling very well in terms of performance. Maybe you get benefits from more system architecture, like heterogeneous processors, specialized things better. Even though the transistors are not becoming better, at least use those transistors more wisely, right? It's kind of like that. It's a more system level perspective. So we're going to talk about DRAM in this course a little bit more later also. But DRAM really stores charge in this capacitor. It's charge-based memory. And for this to work, and then there's the access transistor that enables access if you enable the word line over here. And then there's a bit line. Essentially, you connect the capacitor to the bit line as we've shown in the past, right? So for this to work, all of these structures need to work. The capacitor needs to be large enough for reliable sensing. The access transistor and the sense amplifier and the sensing circuitry needs to be good enough for essentially leakage, low leakage and high retention time. And people have argued that scaling beyond some nanometers, some feature sizes, has been challenging. Sorry, and that's true. It's become harder and harder to scale DRAM to future technology nodes. Right. And if you want to really look at DRAM, it kind of looks different underneath. So people actually try very hard, or people meaning DRAM manufacturers try very hard to etch the capacitor so that the capacitor is very thin and doesn't occupy a lot of area. So it's really three-dimensional. And it's really the access transistor and other stuff that's occupying the area in the two-dimensional space, all the capacitor, also the width, right? So it's very fascinating that people actually come to this point in manufacturing these chips. But when you actually reduce the size of the cell, both of these properties that I mentioned become difficult to maintain. Essentially, reliable sensing and high retention time, they both reduce over time. And this manifests itself as errors. And we've always been interested in these errors. This is a study that we did with Facebook some number of years ago. We essentially analyzed all of the memory errors in all of Facebook's servers worldwide. And even at that time, they had a lot of memory, a lot of infrastructure, a lot of servers. They didn't allow us to write how much memory, how many servers that we examined, because they thought this would reveal their infrastructure, which could affect their stock price and competitors, or etc. But it's a lot of memory, essentially. So this is very statistically significant results. And this is one thing that we found. Essentially, this shows a correlation between the density of the chip that's employed in the server and the failure rate that is observed in the field in the server. These are production data center servers. Essentially, they're running production workloads. And you can see a clear correlation, even though you don't quite understand this metric. You can read the paper and understand it, but it's what it says, essentially. Computation of it is not easy, but that's how it is. Essentially, if you employ a denser DRAM chip, the server fails more frequently. And the reason, likely reason is that these chips have more failures, right? Because they're denser DRAM chips, they're 4 gigabit chips in this case. The cells are smaller and cells are closer to each other. So you get more failures. And there's a lot more analysis in this paper if you're interested. Well, it's always good to do this large scale analysis to understand the trends in computing infrastructure, right? Okay, then we also were very interested in understanding a lot of issues in DRAM, especially retention time to begin with, but then many other things. So we really wanted to build an infrastructure to test these issues at the small scale as opposed to this large scale. Because if you have a large scale production system, first, you may not have access. And even if you have access to it, as we did together with our collaborators, then you cannot control things, right? You can actually observe things, but you cannot control. And observation is not enough, because observation without a controlled environment is not an experiment. It's really case studies anymore. And case studies are always interesting, but you cannot pinpoint causes in a case study, right? You can, of course, argue that some things may be happening, but you cannot pinpoint. So to be able to pinpoint causes, you need to do experiments, and experiments require control. And this is a system that we built to enable control. And to enable control, in this case, we use FPGAs, and we modify the memory controller so that we can actually do anything to the memory controller, legal or illegal. We can try anything, basically, with our own memory controller. You cannot do that with a CPU, where you cannot control the memory controller, right? You can indirectly control the memory controller in a CPU by doing load store instructions or other stuff if you're careful, but you don't have access to direct control. So we wanted direct control. So you can turn off refresh, for example, and see what happens. And this is the infrastructure where we did a lot of RowHammer experiments on. This is the open source infrastructure, and it's actually relatively easy to use. It has C++ API, etc., flexible. And this is a more recent one that works for DDR4 as well as HBM chips. And both of these are, and all of these are actually, I should update the slide with HBM stuff. So Ataberk is a task right now to add the HBM boards that work with this, because when we actually released the paper, it was working with DDR4, but now we have an HBM2 version that's working, that's also released completely openly. So hopefully people take it and do something good with it. Okay, so one of the main reasons why we built this infrastructure was to study technology scaling issues. And one of the main technology scaling issues at the time, and I believe still, is data retention, meaning how long can you retain data in this memory cell? Right? And this is, I think, fascinating because we refresh memory very frequently, right? Today, every 64 milliseconds. Actually, in recent standards, it's gone down to 32 milliseconds. So scaling is actually making this worse, clearly in real data also. Probably it will go down to 16 milliseconds in future technologies, maybe 8 milliseconds, But this is a very frequent refresh. Basically, you're frequently refreshing everything in memory. And this is clearly causing energy, performance, quality of service. We said, maybe we should try to get rid of refresh so that we don't need to deal with it. And we again took a system level approach. If you take a system level approach, maybe if you understand the device nicely, you can get rid of refresh. There are other system level approaches you can take also. But basically, we knew from previous papers that retention time profile of DRAM looks like this, kind of. Basically, most of the cells don't require refresh as frequently as the standard suggests. Most of the cells can actually tolerate not being refreshed for 256 milliseconds, which is 4x the interval at which you're required to refresh DRAM today as defined by the standard. Which means that if this is true, and if you can expose this to the memory controller, you can actually get rid of refresh, most of the refreshes, more than 75%, as you can see, right? That's the idea over here. Now, we published this work, but then we realized using our infrastructure that this is not that easy, because not only the refresh retention time, how long a cell retains data is dependent on the location of the cell in the chip, which you need to identify. But it's also dependent on the value stored in that cell and the value stored in the cells around it, because this determines capacitive coupling between the cells. There's a lot of electrical interference between the cells and the wires used for accessing cells, which means that this retention time is a dynamic value right now that's dependent on the value that's stored in the cell. That's not terrible. What's really terrible is this really a random value. Not all the time, but in some cases, there are cells that would switch from a very high retention time for a very low retention time. And there's no real, and this happens because of trap-assistant gate-induced drain leakage, which is a process that's essentially a random process. So the trap happens and that trap gets filled, and then a cell loses its charge quickly. And this is a random process as far as we know. Meaning that this is not very easy to do. If you want to figure out which cells retain data, how long you need to keep doing this dynamically while the system is running. You cannot have a static profile. So we publish papers, although it's always good to have a paper that's not necessarily solving all of those problems. This is the paper that we published in 2012 that basically assumed that that profiling is done. If that profiling is done, this is what you would get. And you can see that people are very interested in this paper because they selected it for a special issue of like 25 years of ISCA, as you can see, last year. And I still like this paper. A paper doesn't need to solve every issue that's out there. As long as it brings about some new idea and it provides some new insight, it can actually enable a lot of progress. And after we wrote this paper, we also said, okay, let's test what we wrote. And that's what led to this paper saying that, oh, it's very difficult to do this in real life. So we provided some solution directions. And then over time, we actually tried to solve this problem. And we have actually some solutions right now that are much better than the past. I'm not going to talk about this. When we have the data retention, et cetera, lectures, actually, if we have them this year, we will talk about that. So this paper, for example, shows a solution to identifying retention failures using online profiling. You keep profiling DRAM online, figuring out the retention failures, and then adjust your refresh rate accordingly. This was led by Minesh. And it's also the first analysis of LPDDR chips in the field, which is not in the field, but LPDDR chips, period, in real LPDDR chips. And then there are other papers that we've done that I'm not going to talk about. So clearly, the fact that we built this infrastructure enabled us to understand a lot of issues in refresh and data retention. And that was one of our original goals. At the same time, and you can actually watch some of these lectures, it's an earlier incarnation of this computer architecture, as you can see, lecture 2B from fall 2020. We kind of did some reordering of lectures over time. At the same time, we actually had built another infrastructure to test similar scaling issues for NAND flash chips. This is also an infrastructure that's very interesting. We could never open source it because this was actually built together with industry. We had some special, let's say, permissions so that we could actually do this testing, which was, I think, important. It's always good to have industry partners that are looking forward and that are actually interested in progress as opposed to hiding stuff. So I was lucky to have a lot of industry partners that did that actually, and we still have some of them. So basically, with this infrastructure, we were able to look at what's happening in the errors in the flash chips. And this is very fascinating. We'll talk about that later in the course. And we wrote some papers. As you can see, this is one of the earlier papers that essentially revealed a lot of different error patterns in flash memories that are used at the time. We looked at retention characteristics. We look at, and this is a summary of a lot of the work that we've done until 2017 or so. If you're interested in SSDs and error characteristics, this is a really long summary, and hopefully it's a nice summary. But we actually studied a lot of read disturbance characteristics in flash at the same time. So if you look at these earlier papers, we analyzed read disturbance, etc. It was not a huge problem at the time in flash. It became much worse over time. And then, of course, if you're doing these things, the natural question to ask is, what about other issues in DRAM, right? DRAM clearly does not have only retention issues. These other memories have read disturbance. What about the read disturbance in DRAM? Let's analyze that. Let's see if there's a problem, and let's understand if we can solve it. And that's what we essentially did to understand. Essentially, that's what led to RowHammer. And we did this together with Intel folks who actually helped us build some of that infrastructure. So what is RowHammer? Essentially, you can produce these bit flips internally in DRAM. And the idea is very simple. You've seen the subarray level structure of DRAM earlier. Essentially, in order to access one data, you need to activate one row. We apply high voltage to that word line. And then if you want to access some other data in some other row, you need to deactivate this row, apply low voltage to that word line. It's called pre-charge bank in DRAM. And if you keep doing this repeatedly, activate, pre-charge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, it turns out some vulnerable cells, or RowHammer vulnerable cells, in physically adjacent rows flip. They lose their charge. If they were storing 1, they become 0, for example. But you need to be able to do this hammering enough times before the cells get refreshed so that you can corrupt data. Clearly, this should not be happening because this is data corruption. And this is really not specified in the standard clearly, right? Okay, so we call this the hammered row, we call this the victim rows, and we basically said, showed that repeatedly accessing the hammered row causes disturbance errors in most real DRAM chips that we tested. And we tested a lot, and we showed that more than 80% of the DRAM chips from 3 major manufacturers are vulnerable to this phenomenon. There are only 3 major DRAM manufacturers in the world, ABC. Yes. Mm-hmm.
How could this DRAM will be exploited in the current cloud system?
Current what systems?
Current cloud system.
We'll get back to that. We're not. We'll get back to that in the next lecture, probably. Yes. Hold that question. Yes. Yeah. No, yeah, I guess we were being nice. We didn't want to reveal at that time, but you can guess who they are, Samsung, Hynix, Micron. But we didn't want to really cause a situation where one company's chips may be perceived as being worse than another company's chips, okay? Now we tell the company's names because this situation is very widely known, but at that time it could have had a bad impact on one company. Okay, not that I have any interest in that company. I have zero interest in any of those companies, by the way, at that time also. But that's one reason for not telling the names. I think today there's no reason because of the history that happened that you will see in the next lecture. Because I think they're, yeah, okay. I think they didn't really own up to the problem, basically, as they should have, let's say. Okay. But basically, this is a scaling problem, and the chips that we've tested that were manufactured before 2010, we weren't able to induce these bit flips. Every chip that we tested that was manufactured between 2012 and 2013, we were able to induce these bit flips. And these were not the best patterns. Based on what we know today, 10 years down the road, we could have done better at the time. But still, we were able to induce bit flips. This is good. So why is this happening? Essentially, DRAM cells are too close to each other. There's electrical interference. When we activate a row, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row lose a little bit of charge. And if you do this hammering activation enough times, charge in such cells get drained. And that's how you lose data. So you should be able to do this activation enough times within a refresh interval. And this causes bit flips. I'm going to finish this program and then I'm going to stop. But basically, it's not just in the FPGA we were able to show this. We actually showed this in a real CPU. Meaning a real program, real user level program running essentially this code, which we also open sourced. And this program selects addresses X and Y such that they're in the same bank. It basically bypasses the caches in the CPU, bypasses the row buffer in DRAM, such that it keeps activating X and Y in an interleaved manner like this. And if the chip is vulnerable, hopefully you'll get bit flips. Now, this is not the best access pattern. We also showed in the paper that if you actually sandwich one row between X and Y, such that X is on one side and Y is on the other side of the row, you get bit flips earlier and a lot more bit flips. Now, this is called double-sided RowHammer, and people actually exploit that. This is the best known hammering mechanism today, without solutions, of course. And we were able to show that you actually observe errors in real systems. So it's a real robustness issue, including reliability, security, and safety. We argued that in the paper, basically, that people should not have bit flips like this. And the first takers was memory testing people. These memory testing people read our paper. They basically immediately implement a RowHammer test. People were not testing for this issue in memory testing. Testing meaning like when you get a computer and you run a memory test, memtest 86 is a program that tests your memory. They added this test, and then if you read what they say over here, they had to add something to their web page to soothe people. They basically said, if you're getting errors during test 13, these are most certainly real errors. They're RowHammer errors, and read this paper, etc. So basically, it was added because of this. I will finish at the end of the slide, but we basically said that this should not be happening. And I still think this should not be happening. In a real chip, this should not be happening. And access to one memory address should not have unintended side effects on data stored in other addresses. And we said that someone can take this program to hijack your computer. So someone can actually cause an attack. And these good folks from Google Project Zero did essentially that 1 year, well, less than 1 year later. They basically read our paper, and they basically crafted an attack in which a user-level program can induce bit flips in its own page table that points to its own page table. And if you are able to flip the right bits in your own page table, you can get write access or modification access to your own page table. Well, that's a high-level description of it. There's a low-level description that we had in DDC actually, but I'm not going to show over here. But basically, I'm going to finish with this slide. Essentially, there are many security exploits. One can exploit RowHammer to take over a system, read data you don't have access to, break out of virtual machine sandboxes, or corrupt important data, like rendering ML inference useless because you corrupt some important weight such that your inference is not accurate anymore. Or you can steal secret data like cryptographic keys or ML model parameters, and who knows what else. Okay, and we're going to continue this, both the security aspects and also analysis aspects and solutions in the next lectures. Okay, you have a burning question? Go ahead. Yeah, okay. Yeah, you cannot control that. It's basically a function of which bit is vulnerable. But security folks are smart enough to figure out how to land security critical data to places where things are vulnerable as much as they can. So in the end, it becomes a probabilistic attack. You cannot control the bit that's vulnerable, but you can control the data that's placed in some of those vulnerable bits.
So we just damage or corrupt the data, but we cannot change it in a way that we want precisely, right?
Not precisely, but you can change it probabilistically. Yeah, that's what it causes a security attack. If you can change it in a probabilistic way such that you can take over a system at some point. Yeah. Okay. Yes.
What about stealing? Like, how do you steal the row? Would you attack what you didn't really access the readers to?
Okay, let's leave that to next week. But basic idea is, like you can read data that you don't have access to, right? That basically you can guess based on. So RowHammer has this property of data pattern dependence. Some data patterns are much more vulnerable to RowHammer, and you can guess what data is stored in a nearby row by actually causing RowHammer to not that row, but the row next to it. This is called RAMBleed. It's a paper, and they basically have this attack. I think next week we'll discuss these more, and you can have more detailed questions. Okay, one more. That's a question for next week. They tried initially, and now they're trying harder. So they tried initially, and we showed that their solutions are not good enough, not secure. Basically, we could induce bit flips in chips that they claimed are RowHammer free. They boldly claimed that, and that claim was broken. Let's say after that we started saying their names, basically, because I think they deserved it at that point. But Right now, there's a lot more effort to solve it. In fact, the DDR5 standard introduces a much more rigorous solution. It's going to become harder and harder, but I believe there's still gaps. And we will discuss those gaps in the next lectures. Okay. Okay. I'll see you all next week. Have a good weekend.